weren't here, they won't hear the announcement. I usually record those too, but not now. Yuck. Okay, from current slide. And I think we did this slide last time, didn't we? I know we did that example. Okay. And I think I just read this slide, but we didn't do much more with it. Okay? So, if you run into a function that looks impossible to take a derivative, okay, you might consider, but it's something that you can easily take a log, take the log of it, take its derivative, and then go backwards, okay? And this next example hopefully will show that. Here is example 6. Okay. All right. Anyone want to take a derivative of that one right off the top? It's doable, by the way. It is doable. What would you need to use? The quotient rule. And that is going to involve a good amount of chain rule and power rule and other stuff, okay? And let's see, do they actually do it? No, they don't, okay? So, let's try taking a log first, okay? Let me get my pen. Or do you want to just, for funsies, see what that derivative is going to look like? You do, yeah. I was hoping you'd say no. Okay. Huh?
I was joking. Let's do it.
Yeah. Huh? Let's do it. Okay. Let's see if we can do y prime. Y prime would then be, how does the quotient rule go?
The bottom.
Yeah, low d high. So that would be the square root of x squared plus 1 times the derivative of the numerator, which is? Yeah, we're doing the d high now. So what's the derivative of the numerator? Okay. That's a power rule here. Yeah. 2 times x minus 2. Right? I put the 2 way out front just because the derivative of the numerator is 2 times this to the first power times the derivative inside is just dx. So yeah, that's all it is. 2 times x plus 2. Minus high d low, which is x minus 2 squared. And then what's the derivative of the denominator? Now, I'm going to rewrite the denominator as x squared plus 1 to the 1/2. I normally would say negative 1/2, but we're doing d low, so let's just leave it as 1/2. And what's the derivative of that? One half. Say again?
1/2 x squared plus 1.
X squared plus 1 to the minus 1/2. Missing something. Chain rule.
Oh, and that's why I couldn't figure out why we didn't do the chain rule on the...
Well, we sort of did, but the derivative of x is x. Yeah. So, I mean, derivative of x is dx. So, 1. Yeah, exactly, 1. That's a better way to say it. But here, the derivative of x squared is not 1. It's 2x. So the 2 is going to wipe out the 1/2, and then you're going to have an x in front. Okay, or wherever you want to put it. I found it more convenient though there. Over low, which is x squared plus 1, right? When you square a square root, you lose the square root, right? All right, now let's see what we've got here. Okay, this is 2 times the square root of x squared plus 1 times x minus 2 minus x times x minus 2 squared over the square root of x squared plus 1 all over x squared plus 1. Okay? Now that's pretty messy looking. So we could multiply and divide this by the square root of x squared plus 1.
The wire shot.
The wire. Okay, the cable.
Yep.
Okay.
So
Everything else is okay.
Yes, everything else is okay. Good. That classroom no longer has a wire because I took theirs.
Right.
And
Okay.
this is the broken
Yeah,
wire.
and I will, wish I had something to mark that as bad.
I got it. Give me a
Okay.
second. I'll get it.
Okay, or just throw it in the trash can.
Well, you're gonna probably need. Do you need to go get a new one from the desk?
Well, I was going down to Miss Glass, Jamie Glass, you know where our office is?
Mm-hmm.
You do?
Yes.
Tell her this one, I
You need to
messed it
replace
up and it needs to be replaced. She dug to find that one for me, so if she can find another one, we'll take it up there. If not, I do know where there's another one. Okay, and I'll get it after class.
Just was.
Thank you so much.
Absolutely.
Oh, wait, no, wait. Oh, yeah, this is, okay.
Yes,
I know what this is now. Okay. I was holding this in my hand, said, what is this? Okay. I'm so sorry. One of these days we'll get class done. All right. Now, did you note what I was trying to say? See, this has a denominator here, this one doesn't. So if we multiply this denominator by square root of x squared plus 1, but then we have to multiply the numerator by square root of x squared plus 1, which loses the radical, but you have this down here. Do you follow that? Is that okay? All right. So this will be a square root of x squared plus 1 down here, and at the same time losing the radical up here. Okay. Now, since we have, and all this is over common denominator, we can move that downstairs now and make this to the 3 halves power. Right? Lose these two, move it downstairs, and now it's to the 3 halves power. Okay with that? Too much sleight of hand here? Okay. Now let's see what we can do to the numerator. Oh, man, who wants to do anything to this? Okay. I'm cheating big time here. Going to leave the answer as similar to this as I can to what they're going to get later. Okay? Now, I notice there is a factor of x minus 2 in both of those numerators. In fact, everything that's up there now. So I'm going to factor that out. X minus 2. Okay? So this goes and one of those goes. Okay? And that leaves me with a 2x squared plus 1. Right? Nope, 2 plus 2, sorry. 2x squared plus 2, when you distribute that, minus an x squared plus 2x. Okay, now that was a lot of sleight of hand there. Okay, now this is where I pulled it off before, and I don't want to do that again. So this, I think, is a longer chord, which is kind of a pain in the neck, but maybe it'll be okay down there. Okay, so we factored out the x minus 2 put out up front. Then we had 2x plus 2 here, minus x squared plus 2x. Okay, follow that? Okay, well, let's see what that leaves us with. And this is all over this thing to the 3/2 power. Okay, so this isn't as bad as I thought it was going to be. X minus 2 times, and here's a 2x squared minus x squared, so that's just going to be 1x squared. So that would be x squared plus 2x plus 2 over x squared plus 1 to the 3/2 power. And that's exactly what they got as their y prime. So that's how we do it using product rule, chain rule, power rule, all those rules. Okay? Math rules, right? Yeah, never mind. No, that's what they put on my computer. Okay. And that is the derivative. That's your y prime. Okay? So it wasn't impossible. It was just a little messy with lots of tricks and tracks, but it worked. Now, let's see if it gets any better taking a log. Okay? I'll let you finish writing that. And you can vote on it and tell me which one you'd prefer to do. Everybody got it? You know, you're still writing? Okay. Okay? All right. So let me erase all this scratch. Okay? Now let's first take a log. Log of y is equal to, well, what's the log of this thing? That would be the log of, and I'm going to write it out. You don't have to do this many steps, but I'm going to write it out. X minus 2 squared over the square root of x squared plus 1. And by the way, I've been puzzling over this for a moment. Notice they say x can't equal 2. Okay? Usually we look at radicals and denominators, but the radical's not bothered by x equal 2. The denominator's not bothered by x equal 2. The only thing that's bothered by x equal 2 is the numerator. X can't be 2 there. That would make the numerator 0. Okay? And then if it was 0, the derivative would be probably 0, so it doesn't matter, but there's a reason they did that. We haven't gotten there yet, but there is a reason. We'll see the reason in a few minutes. Okay? So what is the log of all that? You remember the rules for logarithm? Want me to write them out in gory detail? Well, for a quotient, the log of a quotient is the difference in the logs. So that'd be the log of x minus 2 squared minus the log of the square root. I'm going to go on and not use square root anymore. I like to deal with exponential notation, not radical notation. I'm going to write this x squared plus 1 to the 1/2 power. Do you buy that? Okay. Now, do you remember another rule for logarithm? That the log of a power is that power times the log. So that would be 2 times the log of x minus 2. Minus, same thing here, 1/2 the log of x squared plus 1. Okay? You got that? Now, you might could have done that in 1 or 2 steps rather than 3 steps, but do it however you need to. But that's what this is, the log of it. Now what we want to do is take a derivative. Okay? Now, if you take the derivative of this thing, that is going to be, remember, flip back where was it? Goodness gracious. Just did it. Okay. Yeah. If you look back on the previous page, 318, the derivative of the natural log function, number 2, d by dx of log u, we've got log y, is u prime over u. Okay? I mean, just do a chain rule. Derivative of y is d by dx of this would be 1 over y times y prime. Chain rule, okay? So that's what that becomes. Now take the derivative with respect to x of this, and that's going to be 2 times derivative of log x minus 2. What's that derivative? One over this. Derivative of log is 1 over, derivative of log x is 1 over x. So this would be 1 over x minus 2. Okay? Minus 1/2, and then derivative of that would be 1 over x squared plus 1, but now you got a chain rule times 2x. Right? Okay. Now, and this 2 and that 2 disappear. Okay? So now what we have is, well, the next thing I want to do is multiply both sides by y. Why not? Okay? Those go away. Now you got your y prime, which is exactly what we're looking for, equal to y, which was x minus 2 squared over the square root of x squared plus 1. That's what your y was, times this stuff. 2 over x minus 2 minus x over x squared plus 1. Okay. Now, doesn't look much like what we had before, but we can fiddle around with this a little bit, get common denominators, which basically is just going to be the product of those two things, right? So this is going to be...
Do that in that last step one more time. I was right, and I looked up in the middle of it.
Oh, okay. All right. This was y prime over y, right? Okay. Is equal to that part. And then what I did was multiply both sides of the equation by y. Okay? Okay, so the y's go out here. That leaves me y prime, which is just what we're looking for. But then rather than y, I'm going to write what y is. X minus 2 squared over the square root of x plus 1. X squared plus 1. Then times what was left here, which is 2 over x minus 2 minus x over x squared plus 1. Oh, the 2's come out. Okay, they could date. All right, now, I want to get this over least common denominator, which is the product of this times that. Okay? So, I'm running out of room. So this thing right here, I'm going to write it back as y again. And I'm going to bring it back in again because I just don't have room to write it. So let me write that as y again and do this here. Okay, least common denominator is going to be x minus 2 times x squared plus 1. Okay, and to do that, I'm going to need to multiply the x squared plus 1 times the 2. That would be 2x squared plus 2 minus, and x times x minus 2 is minus x squared plus 2x. That should sound sort of familiar, right? Same numerator we had before. When you subtract the x squared, you lose that 2, and this gives you x squared plus 2x plus 2. Okay? Now, this probably seems like cheating, and it probably is, but okay, that's part. Now the y, remember, was this thing over here. Okay, I just didn't have room to write it again. But notice the x minus 2 cancels out one of those x minus 2's, right? I'm just multiplying by y, but I'm doing it over here because I didn't have room to do it. Okay? So what that leaves us with is the y prime from here is equal to x minus 2, we wiped out one of them, times the x squared plus 2x plus 2. So there's your numerator, this times that, okay? Now, the denominator is this times that, which is x squared plus 1 to the 3/2 power. Because this is to 2/2, that's to the 1/2. That would be x squared plus 1 to the 3/2. Okay? Now, we took a few extra steps there, but by and large, the conduct of this, of taking the derivatives, was much simpler because taking derivatives of logs are really easy. Okay? Before, we had square roots and powers and all sorts of things to do, and it made it really messy. But we got the same answer either way. Pay your money, take your choice. You've already paid your money, so take your choice, which one you want to go by and use it. Using the logarithmic differentiation, to me, is a little easier, and because I can skip a few of those steps that I showed you, it's generally faster too. Okay? The last part of both of them is arithmetic, just trying to get least common denominators and all that kind of mess. But it's the same problem. I mean, you basically wound up the same thing that you had before. You had to get the same answer. So, use it if you want to, especially if it gets even worse than that. Now, let's think. Why did they say x can't be equal to 2? Right here. When you take the logs of it, you can't take the log of 0. So this is why you said it can't be equal to 2. With just this, there's no reason to say it can't be equal to 2. Okay? But if you're going to do logarithmic differentiation, you can't ever take the log of 0 or a negative number. Which makes me think, why in the world didn't they say x has to be greater than 2? That's what they should have said, not just can't equal 2. X has to be greater than 2. I guess they didn't want to restrict it because you can't do this either if it's less than 2. Because then that would be a negative number. So, frankly, I think this should have been greater than 2, not equal to 2. To use the logarithm. And that is an issue, if this is going to remove some of your domain, then you probably don't use logarithmic differentiation. Go to the full board.
And can we do the last part again
Okay. Down here?
Yes, sir.
Okay. This was our y, and this was the thing that we had left here, right?
Right.
I just cleaned it up a little bit. Okay? Well, what I did next was get this over least common denominator. I didn't have room to write this and this, so I just wrote the y instead of this. This y and that are the same things. Okay. Now,
This
you got
one's
this
confusing.
part okay?
Because, well, I mean, the y is what was throwing me off, because I was like, that's y prime, but that equals.
Well, because it was y prime over y, we just multiplied both sides of the y. Now, I put in what y was here, and then realized I didn't have room to write it here, so I put it back to y just to do. So then, rather than canceling things out from here, which I couldn't write it, I kept them out from back there. So that's y. That is the same y. It's just my sloppiness. Weird way of doing it.
Makes sense.
Is that all right then?
Yes, sir.
Okay, so that just gives another tool in your belt using logarithms to simplify some differentiation. All right. Let's see how they did it in case it's any different from what we did. I don't think it'll be much different. They may take a few steps. Note that y is greater than 0 for all x's not equal to. No, I see what they mean. I said it had to be greater than 2. No, I forgot that x minus 2 is squared. But still, it doesn't matter. You wind up with a log of x minus 2, which can never be negative. But they finessed all that away, but they didn't finesse away the 2. So for y greater than 0, y is positive for x not equal to, because the numerator is always positive, the denominator is always positive. Okay? It just is 0 for x equal 2. So you can't take the log of 0 or a negative number. So that's why they said that. So ln would be defined as long as x is not equal to 2. Okay. Begin by taking natural log of each side of the equation. Then apply the logarithmic properties and differentiate implicitly. Solve for y prime. Huh. Now that is strange. What I mean by strange is, what is this vertical line doing there? I see no purpose in it. I guess it's just a typo. Okay, so that's not the original equation. It doesn't need a vertical line there, but it's not doing anything, so just ignore it. Okay, take the log of both sides. So log of y is log of that. And then they skipped the intermediate step and went straight to, it's the difference of the logs and then the power and that kind of stuff. So 2 times the log of x minus 2 minus 1/2 times, because this is actually minus 1/2. Or the log of a quotient is the difference in the logs, so that's where the difference comes at. 1/2 log x squared plus 1. Okay. Now take a derivative of both sides. Okay. Derivative of the left is y prime over y. Okay. I like to actually take the derivative 1 over y times y prime. It's the same thing. Okay. Then this is 2 times 1 over x minus 2, and this is minus 1/2 times. The chain rule will be the 2x and the 1 over this is the log thing. So that gives you that. The 2's will go out there. Okay? And so y prime over y is equal to, well, this, they skipped some steps here. Big time they skipped steps. They got least common denominator. They wiped out the 2, so do that already. Least common denominator between these two is the product of those two. Okay? And to get this product, you multiply this one by this numerator, this one by that numerator. Okay? So that would be this times that denominator would be 2x squared plus 2, so there's an x squared and a plus 2, that's where those come from, minus, and the 2's went out, x plus 2 plus 2x. Plus x plus 2x. And so that's where the 2x and the minus x took away one of those, so you have x and 2. They got the same thing we did. Then they multiplied by y, which is what you had up top. And let's see them do that. Well, they wrote it in here, and then they multiplied it, okay? The y is this. And one of these x minus 2's cancel out. We get 1 x minus 2 left. And then the denominator, this one goes, so your denominator is now this to the 1 half times this to the 2 halves, so that would be that to the 3 halves. And it would be x minus 2 times that over this thing to the 3 halves, which is exactly what we got before. Okay? Written as simply as I can think of writing. Okay. Did the same thing we did. They skipped some steps I showed you, and they smartly waited and put the y in at the very end, which I wound up doing, but I introduced it too early. Okay. Any questions on it? I mean, any parts of this that you don't see how they got it? They skipped a lot of steps. I'll grant them that. They did skip steps. And not tell you how they got from one to the next, but you can't fill in the blanks. Okay. All right. Everybody got it? Good deal. All right. Flipping to the next page, because the natural logarithm is defined for negative, is undefined for negative numbers, or 0, you will often encounter expressions in the form of log absolute value of u. Because you can't let that variable u ever be negative. So therefore put it in absolute value. And it keeps it from being negative. Unfortunately, it doesn't keep it from being 0, so you still have to watch out for that. The next theorem states that you can differentiate functions in that form as though the absolute value notation was not present. Whoa, how do you do that? Derivative involving absolute value. If u is a differentiable function of x such that u is not equal to 0, notice u can't be 0, then d by dx of absolute, the log of absolute value u is simply u prime over u. Now, you might say, how can they do that? Well, if you think about it, if u is negative, right? Okay? No, that's not quite true. I was going to say u prime then would be negative as well. And that's not necessarily true. You could have u being negative down here, but u prime being positive, or u being negative. Yeah, so I don't know that you can say that. I thought I'd see a shortcut there, but it's not. They do a little proof there at the bottom, which is basically almost doing what I did. It does come out being, if you go back, way back to theorem 5.3, you'll see that minus sign does carry through, so you can do that. Do they do example 7? Yes, they do. Let's do example 7. Find the derivative of f of x when that's equal to log absolute value cosine. Now, by the way, that is going to be, let me just draw you what that function looks like. Okay? Every time it would go negative, it pops it positive again. Now, the problem with this is at x equal pi halves, and every half pi, cosine is equal to 0. So you have to exclude those. You can't have those. But let's see what happens. What is f prime then? According to what we just said, 1 over cosine theta x, right? Derivative of log is 1 over times derivative of cosine x, which is what? Negative what?
Negative sine x.
Negative sine of x. Negative sine of x. Okay. Which is negative tangent x. Okay? And tangent x is not defined for any half pi. So, absolutely. Well, as soon as you do 1 over cosine x, you have to eliminate all the half pi's. So, yeah, that's taken care of in no problem. So, the derivative is minus tangent x. Because the derivative of this is a positive value, but tangent goes like this, so the negative tangent goes like this, so yeah, that would work. The derivative of this is a negative value, the tangent x would go like this, but negative tangent x like this. So sure enough, that looks like that works perfectly. Of course, x can't be any of your half pi's, because cosine x would be 0 there, tangent is undefined there, so that would be it. Now that's my rendition of it. Let's see how they do it. I'll erase my chicken scratch here and see what they get. Using theorem 5.4, let u equal cosine x and write d by dx of log cosine x would be u prime over u, which is exactly right. But why do that? I mean, why not say log of absolute value u would be u prime over u? That would, but it's fine. I mean, what they said is correct, but once you did that, why put cosine x back in there? Just let it be u over, just put u there. And then you would have that, and that would be minus sine x over cosine x, which is negative tangent x. And of course, negative tangent x is not defined at any of your half pi's. So that was taken care of. They skipped example 8. So let's us do example 8. Locate the relative extrema of this. Y is equal to log of x squared plus 2x plus 3. The relative extrema of that. Well, how do we find our relative extrema? Going back to Cal 1. How do we do it? Second, take a derivative. So dy dx is equal to what? 1 over x squared plus 2x plus 3, 1 over the argument there. But then you got to do the
derivative of the inside.
Yeah, derivative of the inside would be not that hard. 2x plus 2. Perfect. Okay? Now, you took a derivative, but how does that give you the extrema?
See where it's equal to 0?
Yes, you said it equal to 0. Now, how can you make that thing equal 0? Only one way, making the numerator equal 0. That's the only way to get that to be 0. Who cares what the denominator is? It doesn't matter. You want the numerator to be 0 for that expression to be 0. So basically, you set 2x plus 2 equals 0, and what does that give you? Yeah, x equal negative 1. Okay? You can just look at it and see that, or subtract 2 from both sides, divide by 2. So sure enough, x equals negative 1. That is your one and only local extrema. Okay. Usually, though, you list the extrema as an xy pair, so you do need to plug that back in to your original function. So that'd be y is equal to the log of, what happens when you put a -1 in there? That becomes 1 minus 2 plus 3, and that would be log of 1 plus 3 is 4 minus 2 is 2 today, anyway. Okay. So the y value is that, so your local extrema is -1 log 2. And then they show the graph in the text, and you see there is one place and one place only where you have a relative minimum.
So, let's have something we need to help understand it here. Like instead of having -1 f -1, it's now like I mean, how do you get the? I'm trying to figure out what I'm trying to say. Like,
yeah. Well, here's your function, and when x equals -1, you know that's where your first root is 0. Plug that in, and that gives you your y, and that's exactly what we did here. That gives you the y value, log 2. So unfortunately, it's not a very pretty number. It's an irrational number, but it is a number.
It's an irrational number.
What's that?
I was saying it was an irrational number.
It's
Like
not.
it-
Oh, if it was, doesn't make a difference. Just a number.
I was saying it was. Yeah. I was asking it is an irrational number because
It is. Yeah. Log 2 is irrational.
Okay.
Yeah. Do it on your calculator and see if.
Error.
No, it doesn't go error. It just goes on and on and on and on and on. No decimal repeating or anything else. It's an irrational number, like pi or like square root of 2 or log 2 is just irrational. Okay, that finishes 5.1. Finally, okay. Let's do the. No, they don't do this. Okay. The concept check is something you can always do anytime. That just sort of brings into your mind what these definitions and things are. But homework exercises do either 5 or 7 or both, and they're both at calcchat.com. I would match all of 9 through 12 with A through D. The thing is, only 9 and 11 are going to have the answers in the back and at calcchat.com, but still, it'd be sort of fun to match them all up. Then, do any of the odds. All right. Oh, man. 13 through 17, they're all at calcchat.com. 17's at CalcView. Do 19, it's at CalcChat and CalcView. Do any of the odds 21 to 29, they're all at CalcChat. 23's at CalcView. Do any of the odds 31 to 35, they're all at CalcChat. 31's at CalcView. Do 37, and do either 39 or 41. All of those are at CalcChat. Do any of the odds 43 through 65. They're all at CalcChat. 45's at CalcView. Do any of the odds 67 to 73. They're all at CalcChat. Do either 75 or 77. They're both at Calc. Or any of the odds 75 to 79. They're all at CalcChat. 77's at CalcView. Do either 81 or 83. They're both at CalcChat. 81's at CalcView. Do 85 is at CalcChat. Do any of the odds 87 to 91. They're all at CalcChat. 87's also at CalcView. And do 93. That's at CalcChat. Exploring concepts. You could think through those 95 and 97. They should be at CalcChat, but if they're not, don't worry with them. There's a couple true false, 99 and 101. Sorry. Oh, man. They're both at CalcChat. Oh, boy. They keep going. you can do any of the odds 103 through 109 if you like, okay? I don't think you have to do any of those, but if you need a little more challenge, there it is. Okay. And they even have a picture of a football stadium. Trying to figure out which one that is. I would say Nebraska because they're all red, but I don't see the N in the middle of the field. That could be Alabama, but I don't know. It doesn't matter. All right. That ends 5-1 finally. So let's move on to 5-2. So, sorry, I said we're going to do these quickly. Today has not been quick by any means at all. The only reason we're doing these at all is I don't know what in the world that is. But I know it's really a distortion of whatever was there before. It's supposed to be. It's just, yeah, it's just messed up. Okay. So let's get off that. 5-2, natural logarithmic functions, integration. Okay. That's sort of what we're doing now. Use the log rule for integration to integrate a rational function. This is just reversing what we've already done. Because we know the derivative with respect to x of log x, even log absolute value x, is 1 over x, right? We've learned that before, okay? And d by dx of log absolute value u is u prime over u, okay? So, to undo those, the antiderivative of 1 over x is log x. Absolute values there, okay? Plus c, you always have to do the plus c for indefinite intervals. And the antiderivative for 1 over u du, well, it's the same thing. This is the same thing. You could put t in here. You could put stickman in there. You could put anything. It's not two different rules. It's the same rule, okay? So I don't know why they listed it twice. The variable is just a dummy variable, and it's the same thing, both of those. So, let's just do an example, okay? Because du is u prime dx, the second formula can also be written as that, and we just did that. I mean, there was nothing, oh, I see. No, before they did 1 over u, now they did u prime over u dx. Okay. That's why they did it, I guess. All right. I really hate that they do the okay. They didn't quite do it all, but they started it for you. Just like before, the constant can be pulled on the outside. Okay? I can't get my pen back. Okay, there we go. And then what's the antiderivative? So this is equal to 2 times what? Antiderivative of 1 over x dx? We just did it? Huh? Nope. Log x. Because the derivative of log x is 1 over x, the antiderivative of 1 over x is log x. Okay? With one exception. Plus c. Exactly. You always have to have the plus c. Okay? That was way too easy, wasn't it? Okay? But, you can take this another step. Using your rule for logarithms, that's the same as the log of x squared plus c. Because you can move your 2 to be the exponent. Remember, the log of a power is the power times the log. Well, so you move it back the other way. Now you lose your absolute value bars. Because who cares? Whatever x is, positive or negative, x squared is going to be positive. This is right. It's just x can't be 0. But of course x can't be 0, can it? You can never divide by 0. So you didn't even have to say that, though it probably would have been a good idea to write it down. X can't be 0. Okay. And anyway, that works. Okay? Now, that's how I did it. Let's see how they do it. Just like we did, 2 times the log of absolute value x plus c. But then you can take the 2, make it the exponent of the absolute value x, but you don't need the absolute value anymore because when you square an x, whether it's positive or negative, you're going to get a positive value. So it's log of x squared plus c. All right. Because x squared cannot be negative, the absolute value notation is unnecessary at that final answer. All right. Before we move to here, let's do example 2. Pretty sure. Yeah. A little more involved, but not much. Find the integral of 1 over 4x minus 1 dx. How would you proceed here? Second?
I was thinking about just how to change the log, bring the 4x and negative 1 out of the denominator. But,
Okay. I'm not absolutely sure what you mean by that. One meaning of it could be absolutely right, the other I'm not sure. Okay. You said pull it out of the denominator, is that what you said? I'm not hearing.
yes.
Okay. In a sense. Okay. Now you don't have to do this, but to me it makes more sense. This looks like a perfect job for substitution. Doesn't it? I mean, if you don't see the answer right off the top, try substitution. What would you do? Let, what's our favorite thing to substitute? U equal, me? Okay, never mind, okay. Equal 4x minus 1. Then what's your next step always? du is equal to? Dx, okay? Well, we have a dx up there, but not a 4dx, so what could we do?
Multiply the whole thing by 4.
Divide. Divide the whole thing by 4, right? So that makes dx equal du over 4. So let's see what we've got now when we did our substitution. We have the integral, and we don't have limits, so we don't have to worry about there. 1 over u, right? Because that was our u. Your dx is du over 4. I'm going to take the 4 on the outside, right? Is that okay? So this is going to be 1/4. And what is the antiderivative of 1 over u du? Second? Oh. Log u. Absolute value of u. Okay. One more thing. Plus c. Okay. But we didn't have u's in our original problem, so let's go back and put them in here. That'd be 1 over 4 times the log of, what was your u? 4x minus 1. There's your answer. Okay? Now, that's almost the same thing as your undoing the chain rule, which is sort of what you're doing. You could just look at this and say, that's going to be log of 4x minus 1, but then you have to take it 1/4 out. I find that students get confused about whether it's going to be a 4 or 1/4. Doing it this way is obviously a 1/4. Okay? I think the other way is 2, but this is more certain. So I like to do a substitution on this. It just makes it so obvious this has to be the answer. Whereas the other way you thought, well, I've got a 4 there. Is it divided or multiplied or whatever? This shows you it has to be divided. Okay? Is that all right? And by the way, they do substitution too. Good for them. That works quite nicely. Okay? Now, I can't remember what was the next thing that was going to show up. It wasn't this. Oh, okay. We still need to do examples 3 and 4. Okay? So let's do those. You okay with them? I mean, you want to do them, or you got this down so well you don't need to do them? Okay. Here's what we got. Find the area of the region bounded by the graph of y is equal to x over x squared plus 1. Okay? The x-axis and the line y is x equal 3. Okay. Now, unfortunately, you almost have to draw the graph to get the full appreciation of this. Okay? Or at least start to draw the graph, like pick some points. What's an obvious first point to pick? Easy x.
3.
Second?
3.
Easier. Easier.
0.
0. I always start with 0 if I can. Well, x equals 0, what is y? 0 over 1, right? Which is 0. Okay. Now, if you do any x less than 0, that will be negative, but this is still positive. So now you're in the negative numbers. And remember they said the x-axis is going to be one of the boundaries. So let's keep everything above the x-axis. So that means this starts at x equals 0. Can't go to the left. So that gives our lower bound. Our right-hand bound is this x equals 3. So we're going to be between x equals 0 and x equals 3. Because everywhere in there, you pick a positive x here, 1, 2, 2.5, 3, anything, and this is going to be positive, that's going to be positive. So you're always positive for any positive x, negative for negative x, so let's not go there. We're going to start at 0 and go to x equals 3. And it stays positive. Okay? So that's going to be the thing. So I didn't draw the graph, but I kind of pictured what it looked like. I don't know how it looks there, but I know it's always positive. So therefore, we can do the integral. What we're asking for, the area bounded by the curve, that will be the integral from 0 to 3 of x over x squared plus 1 dx. Right? Do you buy that? If you look in the book and see the picture, you see it's got to be that. Okay? So, you're all right with it?
I'm offended, but I'll manage.
What's that?
I'm offended, but I'll manage.
Okay. All right. Now, how do we do the integral? What's that?
By substitution.
By what?
Substitution.
Oh, okay. I like it. And what will you substitute?
We substitute x squared. U equals x squared plus 1.
You got it. Okay. Then
Then
du is equal to? Huh? No. Derivative of x squared is 2x, written in differential form, dx. You always do a dx. If you're taking a derivative, it's du dx is equal to 2x. But in differential form, you pull the dx on the other side. So you have all your x's on one side, u's on the other side, just like you do up there. Okay? Now, the problem has an x dx, it doesn't have a 2x dx. So what do? Divide by 2. Okay? So that gets rid of your 2's there, and now I think we're ready to roll. Okay? Except we need to change our limits. You want to do it now or after we write down the integral? I don't care. Do it now. Let's do it now. Okay, so your x is going from 0 to 3, so what's your u going from? When x is 0, what's u? X equals 0, what's u? 1. When x equals 3, what's u? 10. Okay. And then what we have the 1/2 out here that we've factored out. And the x dx is your du over 2, so that's just du. And your x squared plus 1 is your u. Right? Now, can any of you take the antiderivative? That's the 1/2 antiderivative of du over u. Antiderivative of du over u. Been a long time. Hey, we just did it. Okay, if you look back, just look at the page before. Don't even flip a page. The number 2 there, the integral of ln of u, exactly, ln u. But this time it's not a plus c because we have limits, so we go from 1 to 10. Okay, these are u substitutions. That's going to be 1/2. And when you substitute 10, what do you get? Pretty easy. What do you get? Substitute 10 for u. ln 10. Okay, that even rhymes. Okay, minus ln 1. Okay, this is 1/2. Anyone remember what log 1 is? Pretty easy. 0. Yes, it is. It is 0. Log of 1 is 0. So this basically is log 10 over 2. So let's just write it that way. Log 10 over 2. No plus c's in it. That is your area under that curve. Or 1/2 log 10 is how they leave it. 1/2 log 10. And if you plug in what log 10 is and take half of it, they claim it to be something around 1.151 or so. But that's an approximation. That's exact. Okay? That making sense? Okay. Now, ready for example 4?
We're out of time.
Oh, we're out of time. How can it be? Okay. I'm sorry we got such a late start today. Okay. Let's see what we can do for homework exercises. I know you can do any of the odds 5 through 27, I think. I think you can do them all. You might have a little difficulty with 23. Nah. Let me buffer that a little bit. Any of the odds 5 through 11. Any of the odds 5 through 11. They're all at calcchat.com. 9 is at calcview.com. Once we do a few more examples, then you can do all those. So just 5 through 11 for now. Make sense? All right. Oh, my word. I am so sorry today was such a disaster.
But we got through it, so it's good.
What's that?
I said, but we got through it, so it's
Yeah.
good.
Yeah. So I wish we got started earlier. I'm going in this right at the very